Unit 8, rotation, is mostly divided up into about 3 topics. Topic number 1 is angular kinematics. In order to describe angular kinematics, we're just going to take a object that's perhaps experiencing some circular motion on a disk and give it a tangential velocity value, and give our circular motion or disk some sort of radius value like so. We know that there's a tangential velocity, and that tangential velocity will be measured in meters per second, but there's another velocity component to this motion which refers to the angular velocity. Angular velocity is given the symbol essentially a W, and that's going to be in rads per second. Now, rads per second just refers to how much circular motion has the object made, regardless of the total distance traveled by the object. Angular velocity is essentially independent of the total distance traveled. Now, if we were to solve for the total distance traveled by this object over a given amount of time, let's say in meters, to solve for the total distance traveled by the object, we would just say distance is equal to tangential velocity times time. But angular kinematics doesn't deal with distances. Angular kinematics deals with what's known as angular displacement values. Angular displacement is the distance analog in angular values. It's given the symbol theta, and it's read in rads. Angular velocity, time. Angular velocity is given in rads per second, and time's given in second. So you've already seen one, what I would refer to as analog of our kinematic motion, of our kinematic equations. The old version of it, the linear version of it, was dst, and this one's going to be angular displacement is equal to angular velocity times time. Now, these analogs go for all of our kinematic values. So if we were to throw down all of our kinematic values, which we remember from the kinematic equations back, it would look like this. Distance, initial velocity, final velocity, acceleration, and time. Well, now we have angular analog values that we're dealing with regard to our rotational motion. Angular displacement, initial angular velocity, final angular velocity, time, and angular acceleration, which is given just a fancier A. There we go. Let's throw down all appropriate SI units for those angular values. And then they are rads, rad per second, rad per second, rad per second squared, and seconds. Now, before, when we were describing the motion of the disk, we were experiencing a steady angular velocity, a constant angular velocity. So therefore, to discover our angular displacement, we just use the analog to the DST triangle. But can your rotating disk be speeding up or slowing down like a turntable? Well, of course it can, and that's when you have angular acceleration. So to do calculations involving initial angular velocity, angular acceleration, and those sorts of things, we have the Big Four, but it's the angular kinematic version of the old Big Four that we used to work with kinematics. It looks like this. And just like with regular kinematics, this version of that kinematic would not be provided on any AP exam. In order to experience this sort of motion, you have to have a steady angular acceleration. Now let's talk about converting between linear and angular kinematic values. There are 3 predominant points of contact where we can convert between linear and kinematic values. First one, the linear distance covered is equal to the angular displacement times the radius of the circle formed, r. The second one, the tangential velocity experienced by an object is equal to that object's angular velocity times radius, r. And the third one, tangential acceleration, or linear acceleration is another way of putting it, is equal to the angular acceleration of an object times, you guessed it, r. So this is how we convert between angular and steady linear values. That's kind of the basics of angular kinematics. In most problems, you're given some sort of variables and asked to solve for another set of variables. Just remember to always convert your units into rads, or rads per second, and then just go for it with the appropriate kinematic equation.